So today lecture number 8. In lecture number 7, we have discussed about the composite sections, how a composite section behave when it is subjected to loading, and accordingly what will be the load carrying capacity of a composite section, what will be the stresses, etc. Now today in lecture number 8, we will be focusing on analysis of material. It may be bars which is subjected to any type of temperature changes. That means either temperature may rise or temperature may fall, and we are aware that most of the materials, when subjected to temperature changes, then there will be either extension or contraction. So that means if there is a metallic material, there is a metal, if it is subjected to rise of temperature, that means if it is at an initial temperature, suppose T1, and later on due to heat or due to temperature variation, if the temperature of the material raises, then there will be extension in the length of the member. Or if there is fall in temperature, then there may be contraction or compression of the member. That means elongation or compression. So in today's lecture, we will be going through bars subjected to thermal stresses. Thermal means due to temperature changes. So let us go through the concept. When the temperature of a body is raised, or lowered, then there will be deformation in the body in the form of extension or compression. That means if the body is free to deform, that means if there is no restriction on the body, then if body is free to deform, then with the change in temperature, there will be deformation in the body. It may be linear deformation or it may be other type of deformation. Now, if the body is restricted in such a way that it is not free to deform, that means if there is a steel member and it is restricted from the both sides along its longitudinal axis, just like fixed supports, then those supports will resist for any type of extension or compression of the member. So due to this, actually, because there is, suppose let us take an example of there is a steel member and steel member is subjected to rise in temperature, its temperature raised, then it will try to extend, it will try to have elongation. But if the member is restricted from all sides such that it is not free to get expansion or extension, then what will happen? There will be, you can understand in other way, that means support will be resisting the any type of extension or compression. So that means some stresses will be developed, and those stresses are known as temperature stresses, because the region of development of those stresses are due to change in the temperature of the body. Now let us consider if a bar, it may be steel bar, it may be copper bar or any other type of member, is subjected to temperature variation when no extension or compression is allowed. So this will be the case number 1, when no extension is allowed or no compression is allowed. Now let us understand it more effectively. Suppose we take an example of a body. Let L is the original length of the body. It may have initial temperature say T1 degrees Celsius, and let final temperature is T2 degrees Celsius. That means there may be some rise or fall in temperature, and we denote it as delta T. So delta T will be rise or fall in temperature. Let E is Young modulus of elasticity of that material, and alpha is a constant for a particular material, and this alpha is known as coefficient of linear expansion. So as per the physics theory, we know that extension in a member is directly proportional to its initial length. So accordingly, alpha will be the extension in the member. That means coefficient of linear expansion states that it will be extension in the member per unit length of the member. So now see here figure number A. This is the support. That means this member is fixed at left hand end, and this bar, it may be steel or it may be any other material having original length L or initial length L. Now as delta L will be the change in length of the body with temperature. That means if you raise the temperature, then delta L will be increase in length, and if there is decrease in temperature, then delta L may be decrease in length. Now here from A to B, now suppose temperature is raised by delta T and the member is subjected to expansion. Length has been increased by delta L. L was original length, and L plus delta L will be the final length after the raise of temperature. So according to physics theory, this delta L will be equal to alpha delta T into L. That means change in the length is directly proportional to length of the member, original length of the member, directly proportional to how much is the rise in the temperature, and alpha will remain constant for a particular material. So from that formula, we are able to calculate that extension delta L will be equal to alpha delta T into L. Now, if this member is free to expand, then final length will be L plus delta L. Now, consider if we apply a force P inward, you can see in figure C, that means P force is applied inside. So delta L will become 0. So that means you can say that P force is required to bring the extension to 0. That means in figure B, there was extension delta L, and if you can apply force such that you can restrict the extension of this member, then that force will be P. Now this force P can be replaced by here a fixed support. So according to modulus of elasticity theory, Young modulus of elasticity is the ratio of stress to strain, and from that we can find out the formula for load. That means how much force P is required to reduce this extension delta L to 0. So from stress and strain formula, we will be able to get the value of a load. So P will be delta L into A, area of cross section of the member, E is Young modulus, L is the original length, and putting this value here, so putting this value here. Now delta L is equal to alpha delta T and L. When we put here, then you will get the formula that load required is equal to alpha delta T into A into E. So this much force is required. Now if you replace this force P by a fixed end, that means this member is fixed from both the end, and if that fixed end support is able to apply force that is equal to P, which can make the extension 0, then even after the increase of the temperature, raise of the temperature, there will be no extension in the member. Then what will happen? That means you can say support from both the end are compressing the member, and temperature in the member, rise in temperature will try to expand. That means this member will try to expand outside, but support are compressing it. So there will be stresses will be developed in the member. Now in figure D you can understand, here support is fixed support, here support is fixed support. That means this member is restricted to any type of increase in length with a rise in temperature. So ultimately there will be some stresses will be developed, and those stresses will be called as temperature stresses or thermal stresses. So thermal stresses in rod, that stress is equal to force upon area. So that means sigma is equal to P upon A. From that we will get the formula sigma is equal to alpha delta T into E. So this will be the formula for thermal stresses when a member is subjected to delta T rise in temperature, and E is the modulus of elasticity, alpha will be the coefficient of thermal expansion. Then these much stresses will be developed in the member. So that means this stress is directly depends upon alpha. That means this stress depends on the type of the material, whether it is steel, whether it is copper, brass, or any other type of material. Second thing is it depends on the change in temperature. That means how much temperature is increased or decreased, and Young modulus of elasticity. So these three parameters on which thermal stresses will develop. So if this bar is restricted from any type of extension, then this much stress due to rise in temperature will develop. And accordingly thermal strain, that strain is stress upon modulus of elasticity. When you divide this equation by modulus of elasticity, you will get this formula, that is alpha delta T. From this formula itself, it is clear that strain directly depends upon rise in temperature. That means how much, if you go on increasing the temperature, then length will go on increasing. Now bar subjected to thermal stresses again. Second type of condition is when a bar is subjected to temperature variation, but condition is one of the support or two of the supports yields. That means there is yielding of support. So let us consider again same theory. L is the original length of body, delta T rise or fall in temperature, E is Young modulus of the material, modulus of elasticity of the material, alpha is coefficient of linear expansion, delta L is change in length of the body with temperature. So same figure we have taken from the earlier slide. That means there is L is the original length, delta T is the rise in temperature. Accordingly final length of the member will be L plus delta L. So delta L will be given by this formula, that is delta L is equal to alpha delta T into L. Now let the support yield by some delta. Delta is the, it may be in millimeter or it may be in centimeter. So if the support yields, Now let us understand what is the meaning of the yielding. Now see here in figure number C, L was the original length, and initially support was, you can say right hand support was there, and that support has been yielded by some amount delta. That means support itself has yielded by some amount delta. Now if you compare figure number B and figure number C, so you can easily understand that this much is the extension actually happening if the member is free. Now when you have restricted it from both sides, then this extension will become 0, due to which temperature stresses will develop. And when the support yield by delta, which is less than delta L, that means there will be some stresses will again remain in the member, but some of the stresses will be relieved because the support is yielding by delta. That means yielding of the support will be helpful in relieving the stresses. So what will be the actual expansion? Expected or actual expansion required was delta L, but because support itself yielded by delta, then in actual condition, actual expansion due to temperature rise delta T will be equal to delta L minus delta. So this will be the actual expansion. So you can compare it with the previous case when there was no yielding of support. Extension was delta L. Now extension is lesser than initial case. So accordingly stresses will also change. So putting the formula of delta L here, this will be the exact formula for calculating what is the actual expansion. So actual thermal strain will be given by this formula, that is actual expansion divided by L, that means change in actual length divided by original length will be the thermal strain. And from this formula we can easily calculate actual thermal stress, that means actual thermal strain into modulus of elasticity. So these two formulae are very helpful whenever there is a case of yielding of the supports. Now let us take a numerical problem of thermal stresses. A steel rod of 3 cm diameter and 5 meter length is connected between two end supports. That means it is restricted from both the ends. So stresses will develop when temperature is changed. Temperature of the rod is maintained at 95 degrees Celsius. Determine the thermal stresses developed and the pull experienced by rod when temperature fall to 25 degrees Celsius. Now for simplicity, we will be always taking whether the temperature rises or whether temperature falls, same type of diagram, because we want only to understand the concept. So what we have to find out? We have to find out the thermal stresses developed as well as pull experienced by rod with the fall in temperature. First condition is when the ends don't yield, and second is when the end yield by 0.12 centimeter. That means the support has been yielded in second case. Modulus of elasticity again given 2 into 10 raised to power 5 Newton per millimeter square, and coefficient of thermal expansion or linear expansion is 12 into 10 raised to power minus 6 per degree Celsius. So solution of this problem, first of all we will be calculating area of the steel rod, that is because it is a cylindrical type shape. So pi by 4d square we can put for the formula for the area. So area is coming out to be 225 pi millimeter square. Length of rod is given 5 meter, that means 5000 millimeter. Initial temperature T1 of the member is 95 degrees Celsius. Final temperature T2 is 25 degrees Celsius. So there is change in temperature is 70 degree Celsius. So first case number 1, when there is no yielding of support. That means there is 100% restriction, no yielding of support, and it means that extension will be 0. So stresses in the rod will be given by this formula, and after putting the value we are getting the stress in the rod due to rise in temperature is 168 Newton per millimeter square, which is tensile in nature. Now pull in the rod, that means how much force is acting on the rod, that is stress into area 168 into 225 pi. So it will be 118.692 kilonewton. So this much force will be experienced by member when it is subjected to change in temperature, but the member is restricted so that there will not be any extension or compression. So you can see here that L is the length of the member, both ends are fixed, and this arrow, this thin arrow, red color arrow, that means these are the forces which are exerted by the support on the member, and member is maybe trying to contract or expansion depending upon the temperature, and dark arrow is showing that the member, there will be extension in the member. Actually, to understand it, because there is fall in temperature, then what will happen, this member will try to compress inside. That means it will try to compress inside, but due to the restriction of the support, member will not be able to compress. So that means you can say member is subjected to external force due to the support, that is shown by bigger arrow. That means member will be under tension. It is trying to get compressed, but it is not allowed, so it will always remain in tension. So this much force is applicable. Second case, when support yield by 0.12 centimeter, that means 1.2 millimeter. So accordingly, stress, you can use this formula. Stress in the rod will be 120 Newton per millimeter square, which is tensile in nature. Pull in the rod will be 84.78 kilonewton. Now you can compare these two stresses. Stress when the member support is not yielding, then stress is more. When the support yield, then some of the stress will be relieved due to the yielding of the support, and correspondingly load in the member or force in the member will also be decreased. So these type of problems we encounter in civil engineering structure in daily life. That means if there is a steel structure, and in India average temperature at the night generally fall up to 18 degrees Celsius, and maximum temperature, average temperature in India, it may rise up to 52 degrees Celsius. So that means the member will be subjected to rise in temperature as well as fall in temperature. So due to that, there will be some stresses, temperature stresses will always develop in the members, and we have to take care of all stresses so that member should not fail. In lecture number 9, that will be very important lecture, and we will be going through the concept of principal stresses and principal planes, and whatever the concept we will be going to understand in lecture number 9, it will be used throughout civil engineering, whether it is strength of material or whether it is RCC structure, whether it is steel structure. So that's why this lecture number 9 will be very important. So you are recommended and you are advised before lecture number 9 is released, you should go through all the lecture number 1 to number 8 very carefully and try to understand all the concepts, because later on, as we move towards the higher level of strength of material, whatever the concept from in the previous lecture we have discussed from lecture number 1 to lecture number 8, they will be always required to understand the lecture number 9 or lecture number 9 onwards. So it is advised to all of you, go through lecture number 1 to lecture number 8 very carefully, so that you have all the basic concept cleared and strengthening, and you can strengthen yourself with all the basic concepts. Thank you.